This presentation is delivered by the Stanford Center for Professional Development.
So welcome to the last lecture this quarter. What I want to do today is tell you about one final class of reinforcement learning algorithms. First, I want to say a little bit about POMDPs, or partially observable MDPs, and then the main technical topic for today will be policy search algorithms. I'll talk about two specific algorithms essentially called reinforced and called Pegasus, and then we'll wrap up the class. So you recall from the last lecture, I actually started to talk about one specific example of a POMDP, which was this sort of linear dynamical system. Right, this is sort of LQR, linear quadratic regulation problem. But I changed it and said, what if we only have observations YT, right? And what if we couldn't observe the state of the system directly, but had to choose an action only based on, sort of some noisy observations that may be some function of the state. So our strategy last time was that we said that in the fully observable case, we could choose actions, AT equals to, right, that matrix LT times ST. So LT was this matrix of parameters that works out when we describe the dynamic programming algorithm for fine horizon MDPs in the LQR problem. And so we said, if only we knew what the state was, we'd choose actions according to, some matrix LT times the state. And then I said, in the partially observable case, we would compute these estimates. I wrote them as S of t given t, which were our best estimate for what the state is given all the observations. And in particular, talked about a common filter, right, which, and we worked out that our posterior distribution of what the state is given all the observations up to a certain time, that was this. Okay, so this is from last time, said that given the observations y1 through yt, our posterior distribution of the current state st was Gaussian with mean st given t, sigma t given t. And so I said we use a common filter to compute this thing, this st given t, which is going to be our best guess for what the state is currently. And then we choose actions using our estimate for what the state is, rather than using the true state, because we don't know what the true state anymore in this POMDP, right? So, so it turns out that this specific strategy actually allows you to choose optimal actions, allows you to choose actions as well as you possibly can, given that this is a POMDP and given that you have these noisy observations. It turns out that in general, finding optimal policies for POMDPs, finding optimal policies for these sorts of partially observable MDPs is an NP-hard problem. And just to be concrete about the formalism of a POMDP, I should just write it here. Right. A POMDP formally is a tuple right, like that, where the changes are the set Y is the set of possible observations and this O subscript S are the observation distributions. And so at each step, we observe right, so at each step in the POMDP, if we're in some state st, we observe some observation yt drawn from the observation distribution O subscript st that's sort of indexed by what the current state is. And it turns out that computing the optimal policy in the POMDP is an NP-hard problem. For the specific case of the linear dynamical systems with sort of the common filter model, we had this strategy of computing the optimal policy, assuming full observability, and then estimating the states from the observations, and then plugging the two together. And that turns out to be optimal only for that, essentially only for that special case of a POMDP. And in the more general case, that strategy of designing a controller, assuming full observability, and then just estimating the state and plugging the two together. For general POMDPs, that same strategy is often a very reasonable strategy, but it's not always guaranteed to be optimal. Okay, solving these problems in general are NP-hard. Okay. So what I want to do today is actually talk about a different class of reinforcement learning algorithms. These are called policy search algorithms. And in particular, policy search algorithms can be applied equally well to MDPs, to fully observed Markov decision processes, or to these POMDPs, or to these partially observable MDPs. And what I want to do now, I'll actually just describe policy search algorithms applied to MDPs, applied to the fully observable case. And in the end, I'll just briefly describe how you can take policy search algorithms and apply them to POMDPs. Okay? In the latter case, when you apply policy search algorithm to a POMDP, it's going to be hard to guarantee that you get the globally optimal policy, because solving POMDPs in general is NP-hard. But nonetheless, policy search algorithms turns out to be, I think, one of the most effective classes of reinforcement learning algorithms as well, both for MDPs and for POMDPs. Okay. So here's what we're going to do. In policy search, we're going to define some set which are denote capital Pi of policies. And our strategy is to search for a good policy, little pi, in the set capital Pi. Okay? And just by analogy, I want to say, in the same way, back when we were talking about supervised learning, the way we define a set capital Pi of policies and then search for a policy in this set capital Pi is analogous to supervised learning, right, where we define the set script H of hypotheses and search and would search for a good hypothesis in this class script H. Okay, so policy search is sometimes also called direct policy search. And to contrast this with the sorts of algorithms we've been talking about so far, in all the algorithms we've been talking about so far, we would try to find V star, we would try to find the optimal value function. And then we use V star, we use the optimal value function to then try to compute or try to approximate pi star. Right? So in all the approaches we talked about previously, our strategy for finding a good policy was to compute the value function and then go from that to a policy. In contrast, in policy search algorithms, and sometimes called direct policy search algorithms, the idea is that we're going to, quote, directly try to approximate a good policy without going through the intermediate stage of trying to find the value function. Let's see. And also, as I develop policy search, it's sort of just one step that's sometimes slightly confusing. So making an analogy to supervised learning again, when we talk about logistic regression, I said, we have some input features x and some labels y. And I sort of said, let's approximate y using a logistic function of the inputs x. And, at least initially, the logistic function will sort of pull all of the air, right? In the same way, as I define policy search algorithms, there'll sort of be a step where I say, well, let's try to compute the actions. Well, let's try to approximate what a good action is using a logistic function of the state. And so again, I'll sort of pull a function out of the air. I'll sort of say, well, let's just choose a function, and that will be our choice of the policy class. And I'll sort of say, let's take as input the state, and then we'll map it through a logistic function, and then hopefully we'll approximate what's a good function, we'll approximate what is a good action using a logistic function of the state. Okay? So there's that sort of the function or the choice of policy class that's, again, a little bit arbitrary. But it's as arbitrary as it was when we're talking about supervised learning. So to develop our first policy search algorithm, I'm actually going to need the new definition. Okay, so our first policy search algorithm will actually need to work with stochastic policies. And what I mean by stochastic policy is it's going to be a function that maps from the space of states cross actions to real numbers, where pi of s comma a will be interpreted as the probability of taking this action A in some state S. And so we have that sum over A okay. So in other words, for every state, a stochastic policy specifies a probability distribution over the actions. Okay. And so concretely, suppose you are executing some policy pi. Say I have some stochastic policy pi. I want to execute the policy pi. What that means is that in this example, let's say I have 3 actions. What this means is that suppose I'm in some state S, right? I would then compute pi of s comma a1, pi of s comma a2, pi of s comma a3 if I have a free action MDP. And these will be free numbers that sum up to 1. And then my chance of taking action A1 will be equal to this. My chance of taking action A2 will be equal to pi of s comma A2. And my chance of taking action A3 will be equal to this number. So that's what it means to execute a stochastic policy. So as a concrete example, just to make this, the concept of why you want to use stochastic policies may be a little bit hard to understand. So let me just go ahead and give one specific example of what a stochastic policy may look like. And for this example, I'm going to use the inverted pendulum, right, as my modeling example. So there's that problem of balancing a pole, right? You have an inverted pendulum that swings freely, and you want to move the card left and right to keep the pole vertical, right? Let's say my actions. Let's see. And so for today's example, I'm going to use that angle to denote, the angle of the pole phi. And I have 2 actions where A1 is to accelerate left, and A2 is to accelerate right. Oh, actually, no, sorry. Let's write that the other way around. A1 is to accelerate right, A2 is to accelerate left. So let's see. Choose a reward function that penalizes the pole falling over or whatever. And now let's come up with a stochastic policy for this problem, right? So to come up with a class of stochastic policies really means coming up with some class of functions to approximate what action you want to take as a function of the state. And so here's my somewhat arbitrary choice. So I'm going to say that the probability of taking action A1, so it's pi of s comma A1, I'm going to write as, okay, and I just chose a logistic function because it's a convenient function we've used a lot. So I'm going to say that my policy is parameterized by a set of parameters theta. And for any given set of parameters theta, that gives me a stochastic policy. And if I'm executing that policy with parameters theta, that means that the chance of my choosing to accelerate right is given by this number. Okay? And right? And because my chances of executing actions A1 or A2 must sum to 1, this gives me pi of S A2. So just be concrete, right? This means that whenever I'm in some state S, I'm going to compute this number, compute 1 over 1 plus e to minus theta transpose S. And then with this probability, I will execute the accelerate right action. And with 1 minus this probability, I'll execute the accelerate left action. And again, just to give you a sense of why this might be a reasonable thing to do, let's say my state vector is it's this 5D state, and I added an extra 1 as an intercept term just to give my logistic function an extra feature. If I choose my parameters and my policy to be, say, this, right? Then that means that at any state, the probability that, of my taking the action A1, the probability of my taking the accelerate right action, this is 1 over 1 plus e to the minus theta transpose S, which, taking the inner product of theta and S just gives you phi equals 1 over 1 plus e to the minus phi. And so if I choose my parameters theta as follows, what that means is that just depending on the angle phi of my inverted pendulum, right, the chance of my accelerating to the right is just this function of the angle of my inverted pendulum. And so this means, for example, that if my inverted pendulum is leaning far over to the right, then I'm very likely to accelerate to the right to try to catch it. Right? I hope the physics of this inverted pendulum thing makes sense, right? If my pole's leaning over to the right, then I want to accelerate to the right to catch it. And conversely, if phi is negative, is leaning over to the left, then I accelerate to the left to try to catch it. So this is just one example of, for one specific choice of parameters theta. Obviously, this isn't a great policy because it ignores the rest of the features, right? Maybe if the cart is further to the right, you want to be less likely to accelerate to the right. And you can capture that by changing one of these coefficients to take into account the actual position of the cart, and then depending on the velocity of the cart and the angular velocity, you might want to change theta to take into account these other effects as well. That maybe if the pole's leaning far to the right, but is actually on its way to swinging back, specify the angular velocity, then you might be less worried about having to accelerate hard to the right and so on. And so these are the sorts of behavior you can get by varying the parameters theta. And so our goal is to tune the parameters theta. Our goal in policy search is to tune the parameters theta so that when we execute the policy pi subscript theta, the pole stays up as long as possible. Or in other words, our goal is to maximize as a function of theta our goal is to maximize the expected value of the payoff for when we execute the policy pi theta, and want to choose parameters theta to maximize that. Okay. Great. Other questions about the problem setup and policy search and policy clauses or anything? Yeah, see.
If in a case where we have more than two actions, will we use a different theta for each of the distributions, or will we still have the same parameters?
Yeah, right. So what if with more than two actions? Then it turns out, so if you can choose almost anything you want for the policy clause, but you have, say, like a fixed number of discrete actions, I would sometimes use like a softmax parameterization. So similar to so softmax regression, right, that we saw earlier in the clause, you may say that, shoot myself out of space. Right, you may have set of parameters theta 1 through, theta d if you have d actions, and equals e to the theta I transpose s over. Right, so that would be an example of a softmax parameterization for multiple actions. It turns out that if you have continuous actions, you can actually make this be a density over the actions A, and we're parameterized by other things as well. So, but this is the choice of the policy clause is sort of up to you, in the same way that the choice of whether we chose to use a linear function or a linear function with quadratic features or whatever in supervised learning, that was sort of up to us. Right. Anything else? Yeah.
Well, the policy search, the PSA is still stochastic.
Yes.
So is it possible to model stochastic policy using a normal setup with data listing?
I see, right, yeah. Is it so, right, given that MDP has stochastic transition probabilities, is it possible to use deterministic policies and shove the stochasticity into state transition probabilities? The answer is yes, but for the purposes of what I want to show later, that won't be useful, but formally it's possible for if you already have a fixed, yeah, right, yes, if you have a fixed policy, then you'll be able to do that. Yeah. Anything else? Right. Yeah, no, I guess even if your class of policy, you can do that. But for the derivation I need later, I actually need to keep it separate. Okay. Actually, could you just, I know the concept of policy search is sometimes a little confusing. Could you just raise your hand if this makes sense? Oh, cool. Okay, great. Thanks. Okay. So let's talk about an algorithm. And what I'm going to talk about, the first algorithm I'm going to present is sometimes called the reinforced algorithm. What I'm going to present, it turns out, isn't exactly the reinforced algorithm as it was originally presented by the author Ron Williams, but it sort of captures its essence. So here's the idea. In the sequel, and in what I'm about to do, I'm going to assume that S0 is some fixed initial state. Or it turns out if S0 is drawn from some fixed initial state distribution, then everything else A works too. But let's just say S0 is some fixed initial state. So my goal is to maximize this, expected sum of rewards. Right. So given the policy and whatever else, drop that. So the random variables in this expectation is the sequence of states and actions, right? S0, A0, S1, A1, and so on, up to ST, AT are the random variables. So when you write out this expectation explicitly as a sum over all possible state and action sequences of that, okay, so that's what an expectation is, right? Is the probability of the random variables times, that. And let me just expand out this probability. So the probability of seeing this exact sequence of states and actions is, well, is the probability of, the MDP starting in that state. And if this is a deterministic initial state, then all the probability mass would be on one state. Otherwise, there's some distribution over initial states. Then times the probability that you chose action A0 from that state as 0. And then times the probability that the MDP's transition probabilities happen to transition you to state S1 when you chose action A0 and state S0, times the probability that you chose that, right, and so on. And the last term here is that, and then times that. Okay, so what I did was just take this probability of seeing this sequence of states and actions, and I just wrote it explicitly or expanded explicitly like this. It turns out later on I'm going to need to write this sum of rewards a lot, so I'm just going to call this the payoff from now. Okay, so whenever later in this lecture, whenever I write the word payoff, I just mean this sum. Now, so our goal is to maximize the expected payoff, and so our goal is to maximize the sum. Let me actually just skip ahead. I'm going to write down what the final answer is, and then I'll come back and justify the algorithm. So here's the algorithm. So here's the algorithm. This is how we're going to update the parameters of the algorithm. We're going to sample a state action sequence, and the way you do this is you just take your current stochastic policy and you execute it in the MDP, right? So just go ahead and start from some initial state, take a stochastic action according to your current stochastic policy, see where the state transition probably takes you, and so just do that for t time steps, and that's how you sample the state sequence. Then you compute the payoff, and then you perform this update. And so let's go back and figure out what this algorithm is doing. So notice that this algorithm performs stochastic updates, right? Because on every step, it updates data according to this thing on the right-hand side. This thing on the right-hand side depends very much on your payoff and on the state action sequence you saw. Your state action sequence is random. So what I want to do is figure out, so on every step, I'll sort of take a step that's chosen randomly, right? Because it depends on this random state action sequence. So what I want to do is figure out, on average, how does it change the parameters theta. In particular, I want to know what is the expected value of the change to the parameters. Right. So I want to know what is the expected value of this change to my parameters theta. Our goal is to maximize the sum of rewards. Our goal is to maximize the expected value of the payoff. And so long as this expectation is, so long as the updates are on expectation or on average taking us uphill on the expected payoff, then we're happy. And so it turns out that this algorithm is a form of stochastic gradient ascent in which, remember, when I talked about stochastic gradient descent for like least squares regression, so I said that you may have some parameters. Maybe you're trying to minimize a quadratic function, right? Then you may have parameters that will wander around randomly until it gets close to the optimum of this little quadratic surface. It turns out that the reinforced algorithm will be very much like that. It will be a stochastic gradient descent algorithm in which on every step, the step we take is a little bit random. It's determined by the random state action sequence. But on expectation, this turns out to be essentially a gradient descent algorithm. And so it'll do something like this. It'll wander around randomly, but on average, take you towards the optimum. Okay. So let me go ahead and prove that now. And let's see. So what I'm going to do is I'm going to try to derive a gradient ascent update rule for maximizing the expected payoff. And then I'll hopefully show that by deriving a gradient ascent update rule, I end up with this thing in the inner loop on expectation. Okay. So before I do the derivation, let me just remind you of the chain rule, the product rule for differentiation, right, in which if I have a product of functions, right, then the derivative of the product is, given by right, then the derivative of a product of functions is given by, right, taking the derivatives of these things one at a time, right? So first I differentiate with respect to f prime, leaving the other two fixed. Then I differentiate with respect to g, leaving the other two fixed. Then I differentiate with respect to h, so I get h prime, leaving the other two fixed. So that's the product rule for derivatives. And so, let's see. Sorry. If you refer back to this equation, right, earlier we wrote out that the expected payoff can be given by this equation, by this sum over all the states of the probability times the payoff. And so what I'm going to do is take the derivative of this expression with respect to the parameters theta, because I want to do gradient ascent on this function. So I'm going to take the derivative of this function with respect to theta and then try to go uphill on this function. And so using the product rule, when I take the derivative of this function with respect to theta, what I get is, well, I end up with a sum of terms, right? There are a lot of terms here that depend on theta. And so what I'll end up with is I'll end up, having one term that corresponds to the derivative of this, keeping everything else fixed. Then I have one term from derivative of this, keeping everything else fixed. Then I have one term from the derivative of that lost thing, keeping everything else fixed. So just applying the product rule to this. Let's write that down. So I have that. Right. The derivative with respect to theta of the expected value of the payoff is, and it turns out I can actually do this entire derivation in, I don't know, exactly 4 steps, but each of the steps requires a huge amount of writing. So let's watch this. Well, I'll just start writing, we'll see how that goes. But this is a 4-step derivation. Right, so that's the sum over the state action sequences as before. close my bracket, and then times the payoff. Okay. So that huge amount of writing, that was just taking my previous formula and differentiating, these terms that depend on theta one at a time. This is the term with the derivative of the first, pi of theta S0, A0, right? So that's the first derivative term. That's the second one. Then you have the plus dot, 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 bunch of terms inside. And that's my last term. Okay? So that was step 1 of 4. And so by algebra, well, let me just write this down and convince yourself it's true. Right? And so this is the second of 4 steps in which you just convince yourself that if I expand out, take the sum and multiply it by that big product in front, then I get back that sum of terms I get. This is essentially, for example, when I multiply out this product on top with this first ratio, with this first fraction, then pi subscript theta S0, A0, that would cancel out this pi subscript theta S0, A0, and replace it with the derivative with respect to theta, pi theta S0, A0. So this is just algebra, as the same. But that term on top is just what I worked out previously, right, was the joint probability of this state action sequence. And now I have that times that times the payoff, right? And so by the definition of expectation, this is just equal to that thing. Times the payoff. Okay? So this thing inside the expectation, this was exactly the step that we were taking in the inner loop of our sort of reinforced algorithm, roughly the reinforced algorithm. And this proves that the expected value of our change to theta is exactly in the direction of the gradient of our expected payoff. I mean, that's how I started this whole derivation. I said, let's look at our expected payoff and take the derivative of that with respect to theta. And so what we've proved is that on expectation, the step direction I'll take reinforce is exactly the gradient of the thing I'm trying to optimize. And this shows that this algorithm is a stochastic gradient descent algorithm. Okay. I wrote a lot. Why don't you sort of take a minute to look at the equations and sanity check that everything makes sense. I'll erase a couple of boards and then check if your questions after that. questions? Cool. Could you raise your hand if this makes sense? Oh, okay, cool, great. Let's see. So some of the comments, we talked about those value function approximation approaches where you approximate V star, then you go from V star to pi star. Then here we talked about policy search approaches where you try to approximate the policy directly. So let's talk briefly about when either one may be preferable. So it turns out that policy search algorithms are especially effective when you can choose a simple policy class pi, right? So the question really is, for your problem, does there exist a simple function, like a linear function or a logistic function, that maps from features of the state to the action that works pretty well? So a problem like the inverted pendulum, that's quite likely to be true. Going through right, how different choices of parameters, you can say things like that. If your pose leaning towards the right, then accelerate to the right to try to catch it. So things like the inverted pendulum, that's probably true. For lots of what's called low-level control tasks, things like driving a car, the low-level reflexes of, do you steer your car left to avoid another car? Do you steer your car left to follow the curve of the road? Flying a helicopter, again, the very short time scale types of decisions. I like to think of these as decisions like trained operator for like a trained driver or a trained pilot. It would almost be a reflex. These sorts of very quick instinctive things where you map very directly from the input state in action. These are problems for which you can probably choose a reasonable policy class, like a logistic function or something, and it will often work well. In contrast, if you have problems that require long multi-step reasoning, so things like a game of chess, you actually have to reason carefully about, if I do this, then they'll do that, and I'll do this and do that. Those I think of as the less instinctual, maybe high-level decision making, and for problems like that, I would sometimes use the value function approximation approaches instead. Okay, let me say more about this later. The last thing I want to do is actually tell you about. Yeah, I guess just as a side comment. It turns out also that if you have a POMDP, if you have a partially observable MDP, I don't want to say too much about this. It turns out that if you only have an approximation, right? Let's call it S hat of the true state, and so this could be, S hat equals S of t given t from common filter. Then you can still use these sorts of policy search algorithms where you can say pi theta of S hat comma A okay, so then there are various other ways you can use policy search algorithms for POMDPs, but this is one of them where if you only have estimates of the state, you can then choose a policy class that only looks at your estimate of the state to choose the action. And by using the same way of estimating the states in both training and testing, this will usually do something reasonable. So these sorts of policy search algorithms can be applied often reasonably effectively to POMDPs as well. Let's see. Okay, some final words. There's one more algorithm I want to talk about, but some final words on the reinforced algorithm. It turns out reinforced algorithm, it often works well, but is often extremely slow. So it sort of works, but one thing to watch out for is that because you're taking these gradient descent steps that are very noisy, you're sampling a state action sequence, and then you're sort of taking a gradient descent step in sort of essentially a random direction that only on expectation is correct. The gradient descent direction for reinforced can sometimes be a bit noisy, and so it's not that uncommon to need, like 1 million iterations of gradient descent, or 10 million or 100 million iterations of gradient descent for reinforced to converge. So that's just something to watch out for. One consequence of that is that, right, in the reinforced algorithm, I shouldn't really call it reinforce. In what's essentially the reinforced algorithm, there's this step where you need to sample a state action sequence. And so in principle, you could do this on your real robot, right? If you have a robot you're trying to control, you can actually physically initialize it in some state, take an action, and so on, and go from there to sample a state action sequence. But if you need to do this 10 million times, you probably don't want to bash your robot 10 million times, right? And so I personally have seen many more applications of reinforce in simulation. You can easily run 10,000 simulations or 10 million simulations of your robot in simulation maybe, but you might not want to do that. Have your robot physically repeat some action 10 million times. So I personally have seen many more applications of reinforce to learn using a simulator than to actually do this on a physical device. Okay. So the last thing I want to do is tell you about one other algorithm, one final policy search algorithm. Just click the laptop display, please. Okay. There's a policy search algorithm called Pegasus that's actually what we use on our autonomous helicopter flight things for many years. There are some other things we do now. So here's the idea. This is a reminder slide on RL formalism. There's nothing here that you don't know, but I just want to pictorially describe the RL formalism because I'll use that later. So I'm going to draw the reinforcement learning picture as follows. You initialize your system, say helicopter, whatever, in some state S0. You choose an action A0, and then say helicopter dynamics takes you to some new state S1. You choose some other action A1, and so on. And then you have some reward function, which you apply to the sequence of states. You sum that out, and that's your total payoff. Okay? So this is just a picture I want to use to summarize the RL problem. And so our goal is to maximize the expected payoff, which is this, expected sum of rewards. And our goal is to learn a policy, which I'll denote via a green box. And so policy, and I'll switch back to deterministic policies for now. And so my deterministic policy will be some function mapping from the states to the actions. Okay? And so as a concrete example, you imagine that in the policy search setting, you may have a linear class of policies. And so you may imagine that the action A will be, say, a linear function of the states. And your goal is to learn the parameters of a linear function. So imagine trying to do linear regression on policies, except that you're trying to optimize the reinforcement learning objective. Okay, so just very concretely, you imagine that the action A is theta transpose S, and your goal in policy search is to come up with good parameters theta so as to maximize the expected payoff. That would be one setting in which this picture applies. So here's the idea. Quite often, we come up with a model or a simulator for the MDP. And as before, a model or a simulator is just a box that takes as input some state ST, takes as input some action AT, and it outputs some next state ST plus 1 that you might want to take in the MDP. Right? And this ST plus 1 will be a random state. It will be drawn from the random state transition probabilities of the MDP. And this is important. So very often, ST plus 1 will be a random function of ST and AT. In the simulator, this is this box. So for example, for autonomous helicopter flight, you sort of build a simulator, that was typo there, using supervised learning, an algorithm like linear regression or locally weighted linear regression, so you can get a nonlinear model of the dynamics of what ST plus 1 is as a random function of ST and AT. Now, once you have a simulator, given any fixed policy, you can quite straightforwardly evaluate any policy in the simulator, right? So concretely, our goal is to find a policy pi mapping from states to actions. Our goal is to find a green box, find a green box like that works well. And so if you have any one fixed policy pi, you can evaluate the policy pi just using the simulator as via the picture shown at the bottom of the slide. Right, so concretely, you can take your initial state S0, feed it into the policy pi. Your policy pi will output some action A0. You plug it in the simulator. Simulator outputs a random state S1. Feed S1 into the policy, and so on. You get a sequence of states S0 through ST that your helicopter flies through in simulation. Then sum up the rewards, and this gives you an estimate of the expected payoff of the policy, right? And this picture is just a fancy way of saying, fly your helicopter in simulation and see how well it does, and measure the sum of rewards you get on average on the simulator. Right? The picture that I've drawn here assumes that you run your policy through the simulator just once. In general, you would run the policy through the simulator, some number of times and then average to get average over m simulations to get a better estimate of the policy's estimated payoff, expected payoff. And so now that I have a way to, given any one fixed policy, this gives me a way to evaluate the expected payoff of that policy. And so, so reasonably obvious thing you might try to do is then just search for a policy. In other words, search for parameters theta for your policy that gives you high estimated payoff. Right? Does this make sense? So my policy has some parameters theta. So my policy is my actions A are equal to theta transpose S, say, if it's a linear policy. For any fixed value of the parameters theta, I can get an estimate for how good the policy is using the simulator. And so one thing I might try to do is just search for parameters theta to try to maximize my estimated payoff. Okay? So it turns out you can sort of do that, but that idea, as I've just stated, is hard to get to work. And so here's the reason. All right, so simulator allows us to evaluate policy, so let's search for policy with high value. So the difficulty is that the simulator is random, and so every time we evaluate a policy, we get back a very slightly different answer. So in the cartoon below, I want you to imagine that the horizontal axis is the space of policies. So in other words, as I vary the parameters in my policy, I get different points on the horizontal axis here. So as I vary my parameters theta, I get different policies, and so I'm moving along the x-axis. And my total payoff, I'm going to plot on the vertical axis. And the red line in this cartoon is the expected payoff of different policies. Right? So my goal is to find the policy with the highest expected payoff. So you could search for policy with high expected payoff, but every time you evaluate a policy, say I evaluate some policy, then I might get to a point that just by chance looked a little bit better than it should have been. Evaluate a second policy, and just by chance it looks a little bit worse. Evaluate a third policy, fourth, right? Sometimes you look here, sometimes I might actually evaluate exactly the same policy twice, but get back slightly different answers. And this is because my simulator is random, and so when I fly the same policy twice in simulation, I may get back slightly different answers. And so as I evaluate more and more policies, these are the pictures I get. And my goal is to try to optimize the red line. And I hope you appreciate this is a hard problem, especially when all that my optimization algorithm gets to see are these black dots, and I don't have direct access to the red line. Right? So when my input space is some fairly high dimensional space, if I have 10 parameters, the horizontal axis, which actually be a 10D space, and when all I get are these noisy estimates of what the red line is, this is a very hard stochastic optimization problem. So it turns out there's one way to make this optimization problem much easier, and here's the idea. And the method is called Pegasus, which is an acronym for something. I'll tell you later. So the simulator repeatedly makes calls to a random number generator to generate random numbers RT, which are used to simulate the stochastic dynamics. So what I mean by that is that the simulator takes this input a state, an action, and it outputs the next state randomly. And if you peer into the simulator, if you open the box of the simulator and ask, how is my simulator generating these random next states S1, ST plus 1? Well, pretty much the only way to do so, right? Pretty much the only way to write a simulator with random outputs is we're going to make calls to a random number generator and get random numbers, these RTs, and then you have some function that takes this input S0, A0, and the result of your random number generator, and it computes some next state as a function of the inputs and of the random number it got from the random number generator. Right? This is so pretty much the only way anyone implements, any random code, any code that generates random outputs. You make a call to random number generator, and you compute some function of the random number and of your other inputs. And the reason that when you evaluate different policies, you get different answers is because every time you rerun the simulator, you get a different sequence of random numbers from a random number generator. And so you get a different answer every time, even if you evaluate the same policy twice. So here's the idea. Let's say we fix in advance the sequence of random numbers. I'm going to choose R1, R2 up to RT minus 1. Fix a sequence of random numbers in advance, and we'll always use exactly the same sequence of random numbers to evaluate different policies. Okay, so go into your code and fix R1, R2 through RT minus 1. Just choose them randomly once and then fix them forever. If you always use the same sequence of random numbers, then the system is no longer random, and if you evaluate the same policy twice, you get back exactly the same answer. Right? And so these sequences of random numbers, we sometimes call them scenarios, and that Pegasus is an acronym for Policy Evaluation of Gradient and Search Using Scenarios, which I thought was kind of clever. So when you do that, this is the picture you get. As before, the red line is your expected payoff, and by fixing the random numbers, you've defined some estimate of the expected payoff. And as you evaluate different policies, there's still only approximations to the true expected payoff, but at least now you have a deterministic function to optimize, and you can now apply your favorite algorithms, be it gradient ascent or some other sort of stochastic, some sort of local greedy hill climbing search to try to optimize the black curve. And so this gives you a much easier optimization problem, and you can optimize this to find hopefully a good policy. Okay, so this is the Pegasus policy search method. So this, I think, when I start to talk about reinforcement learning, I showed that video of a helicopter flying upside down. So that was actually done using exactly this method, using exactly this policy search algorithm. And this seems to scale well, even to fairly large problems, even to fairly high dimensional state spaces. Typically, Pegasus policy search algorithm has been using, the optimization problem is still is much easier than the stochastic version, but sometimes it's still not entirely trivial. And so we've applied this sort of method with maybe on the order of 10 parameters or tens of parameters, so 30, 40 parameters, but not thousands of parameters. Okay, at least in the sorts of things we've done. Yeah.
So is that method different than just assuming that you know your simulator exactly and just throwing away all the random numbers entirely?
Yeah, right. So, okay, so is this different from assuming that we have a deterministic simulator, right? And so the answer is no. So in the way you do this, for the sake of simplicity, I talked about one sequence of random numbers. What you do is, so imagine that the random numbers are simulating different wind gusts against your helicopter. So what you want to do isn't really evaluate just against one pattern of wind gusts. What you want to do is sample, some set of different patterns of wind gusts and evaluate against all of them in average. So what you do is you actually sample, say, 100, some number I made up, like 100 sequences of random numbers, and every time you want to evaluate a policy, you evaluate it against all 100 sequences of random numbers in an average. This is in exactly the same way that on this earlier picture, you wouldn't necessarily evaluate the policy just once. You evaluate it maybe 100 times in simulation and an average to get a better estimate of the expected reward. And so in the same way, you do that here, but with 100 fixed sequences of random numbers. Does that make sense? Cool. Any other questions? Yeah.
Yeah, if we use 100 scenarios and get an estimate for the policy, in the previous case, if you just run that 100 times with parameters random numbers and sort of you average it, won't you get sort of similar values for both?
Yes, you're right. So the quality, so for a fixed policy, the quality of the approximation is equally good for both cases. The advantage of fixing the random numbers is that you end up with an optimization problem that's much easier, right? So I have some search problem, right? And on the horizontal axis is a space of control policies, and my goal is to find a control policy that maximizes the payoff. The problem with this earlier setting was that, when I evaluate policies, I get these noisy estimates, and then it's just very hard to optimize the red curve if I have these points that are all over the place. And if I evaluate the same policy twice, I don't even get back the same answer. By fixing the random numbers, the algorithm still doesn't get to see the red curve, but at least it's now optimizing a deterministic function. And that makes the optimization problem much easier. Does that make sense? Am I?
So every time you fix this is just what you said, every time you fix the random numbers, you get a nice curve to optimize. And then you change the random numbers to get a bunch of different curves that are easy to optimize. And then you somehow smush them together.
Let's see. I have just one nice black curve that I'm going to optimize. So
for each scenario, right?
I see. So I'm going to average over m scenarios. So I'm going to average over 100. So the black curve here is defined by averaging over a large set of scenarios. Does that make sense? And so there's sort of only one. If the averaging thing doesn't make sense, imagine that there's just one sequence of random numbers. That may be easy to think about. So just fix one sequence of random numbers, and every time I evaluate the policy, I evaluate against the same sequence of random numbers, and that gives me a nice deterministic function to optimize. Okay. Any other questions? Right. And the advantage is really that one way to think about it is when I evaluate the same policy twice, at least I get back the same answer. And so this gives me a deterministic function mapping from parameters of my policy to my estimate of the expected payoff. That at least that's just a function I can try to optimize using a search algorithm. Okay. Other questions? Okay. So we've used this algorithm for inverted hovering, and again, policy search algorithms tend to work well when you can find like a reasonably simple policy mapping from the states to the actions, and this is sort of especially the low-level control tasks, which I think of as sort of quote reflexes almost, right? So concretely, if you want to solve a problem like Tetris, where you might plan ahead a few steps about what's a nice configuration of the board, or something like the game of chess, or problems of long path plannings where you go here, then go there, then go there, then sometimes you might apply a value function method instead. But for tasks like helicopter flight, for low-level control tasks, for the reflexes of driving, of controlling various robots, value function policy search algorithms where it's easier to, we can sometimes more easily approximate the policy directly, works very well. So some final words about the state of RL today. RL algorithms have been applied to a wide range of problems. And the key is really sequential decision making, right? The place where you think about applying reinforcement learning algorithm is when you need to make a decision, then another decision, then another decision. And some of your actions may have long-term consequences. So that's I think of that as the heart of RL, the sequential decision making, where you make multiple decisions, and some of your actions may have long-term consequences. Showing you a bunch of robotics examples. RL is also applied to things like medical decision making, where you may have a patient and you want to choose a sequence of treatments, and you do this now to the patient, then the patient may be in some other state, and you choose to do that later, and so on. Turns out there's a large community of people applying these sorts of tools to queues. So imagine that you have a bank where you have people lining up, and after they go to one cashier, some of them need to go to the manager to deal with something else. You may have a system of multiple people standing in line in multiple queues, and so how do you route people optimally to minimize their waiting time? Turns out there's, and not just people, but so objects on an assembly line and so on. Turns out there's a surprisingly large community working on optimizing queues. I mentioned game playing a little bit already. Things like financial decision making. If you have a large amount of stock, how do you sell off a large amount of, how do you time the selling off of your stock so as to not affect market prices adversely too much, right? And many operations research problems, things like factory automation. Can you design a factory to optimize throughput or minimize costs or whatever? These are all sorts of problems that people are applying reinforcement learning algorithms to. Let me just close with a few robotics examples because they're always fun and we just have these videos. This video was the work of Zico Coulter, our head TA, and Peter Abiel, which is a PhD student here. And they were working on getting a robot dog to climb over difficult rugged terrain. And so using a reinforcement learning algorithm, they applied an approach that's sort of similar to a value function approximation approach, not quite, but similar. They allowed the robot dog to sort of plan ahead multiple steps and sort of carefully choose his footsteps and traverse rugged terrain. And this is really sort of state of the art in terms of what you can get a robotic dog to do. Here's another fun one. It turns out that wheeled robots are very fuel efficient. Cars and trucks are the most fuel efficient robots in the world. Sort of almost. Right? Cars and trucks are very fuel efficient, but legged robots have the ability to traverse more rugged terrain. So this is a robot. This is actually a small scale mock-up of a larger vehicle built by Lockheed Martin. But can you come up with a vehicle that has wheels, so it has the fuel efficiency of wheeled robots, but also has legs, so you can traverse obstacles. So this is so again, using a reinforcement learning algorithm to design a controller for this robot to make it traverse obstacles and these sort of somewhat complex gates that would be very hard to design by hand. But by choosing a reward function, right, tell the robot this is a +1 reward at the top of the go, and a few other things. It learns these sorts of policies automatically. Cool. Last couple fun ones. Show you a couple lost helicopter videos. Let's see. This is the work of, again, PhD students here, Peter Abiel and Adam Coates. Who have been working on autonomous flight. So, you see, I'll just let you watch. Show you one more.
People don't actually do this with a real helicopter, right?
These kind of
I
tests.
see. Not a full-size helicopter, only small radio control helicopters.
But there's nothing, in principle, to stop it from happening for large helicopters, right?
Full-size helicopters aren't designed for this. You still shouldn't do it on a full-size helicopter. Many full-size helicopters would fall apart if you try to do this. Let's see. There's one more. Yes, they're very good human pilots that can. Cool. Just one more. This is just one more maneuver. All right, so that was kind of fun. So this is the work of Peter Abiel and Adam Coates. So that was it. That was all the technical material I want to present in this class. I guess you're all experts on machine learning now. Congratulations. And as I hope you got the sense through this class that this is one of the technologies that's really having a huge impact on science and engineering and industry. And as I said in the first lecture, I think many people use machine learning algorithms dozens of times a day without even knowing about it. based on the projects you've done, I hope that most of you will be able to imagine yourself going out after this class and applying these things to solve a variety of problems. And hopefully some of you will also imagine yourself writing research papers after this class, be it on a novel way to do machine learning or on some way of applying machine learning to a problem that you care about. In fact, looking at the project milestones, I'm actually sure that a large fraction of the projects in this class will be publishable, so I think that's great. Let's see. So, well, I guess many of you will also go into industry, make new products, and make lots of money using learning algorithms. So remember me if that happens. And one of the things I'm excited about is that, you know, through research or industry, I'm actually completely sure that the people in this class in the next few months will apply machine learning algorithms to lots of problems in, you know, industrial management and computer science, things like optimizing computer architectures, network security, robotics, computer vision, to problems in computational biology, to problems in aerospace or understanding natural language, and many more things like that. And so right now I have sort of no idea what all of you are going to do with the learning algorithms you learned about, but every time as I wrap up this class, I always feel sort of very excited and optimistic and hopeful about the sorts of amazing things you'll be able to do. One final thing, let me just give out this handout. Just pass this back. One final thing is that, so machine learning had, can I have one copy, please? Thanks. So one final thing is machine learning has grown out of a larger literature on AI, where there's a desire to build systems that exhibit intelligent behavior, and machine learning is, you know, sort of one of the tools of AI, maybe one that's had a disproportionately large impact. But there are so many other ideas in AI that I hope you go and continue to learn about. And so fortunately, you know, Stanford has one of the best and broadest sets of AI courses, and I hope that you take advantage of some of these courses, go and learn more about AI and more about other fields which often apply learning algorithms to problems in vision, problems in natural language processing, and robotics, and so on. So the handout I just gave out has lists of AI-related courses. It's running down very quickly, I guess. CS221 is an overview of AI that I teach. There are a lot of robotics courses also, 223A, 225A, 225B, I don't know, many robotics courses. You saw many applications of learning algorithms for robotics today. 222 and 227 are knowledge representation and reasoning courses. 228, of all the courses on this list, 228, which Daphne Collar teaches, is probably closest in spirit to 229. And this is one of the courses I highly recommend to all of my PhD students as well. Many other problems also touch on machine learning. On the next page, courses on computer vision, speech recognition, natural language processing, various, you know, tools that aren't just machine learning, but often involve machine learning in many ways. Other aspects of AI, multi-agent systems, taught by, I guess, Yoav Shoham and Mike Genezarov. E364A is convex optimization. It's a class taught by Steve Boyd, and convex optimization came up many times in this class, and if you want to become really good at it, you know, E364A is a great class. And if you're interested in sort of project courses, I also teach a project course next quarter where we spend the whole quarter sort of working on a research project. So I hope you go and sort of take some more of those courses. In closing, let me just say this class has been really fun to teach, and it's actually very satisfying to me personally when we set these insanely difficult homeworks and then, you know, we'd see the solution and I go, oh my God, they actually figured that one out. It's actually very satisfying when I see that. Or look at the milestones, I often go, wow, that's really cool. I'll bet this will be publishable. So I hope you take what you've learned, go forth and do amazing things with learning algorithms. I know this is a heavy workload class, so thank you all very much for the hard work you put into this class and the hard work you put into learning this material. And thank you very much for having been students in this class.